And thanks a lot for being here. Go ahead.
Thanks, Brent. Thank you. Hang on. The bells of Trinity College are ringing in the background to tell me it's 4 o'clock. Let me just wait for them to stop. They go on much longer than you think they would. All right, we're good.
You can't hear them.
No, but I can, so that's the problem. All right, thank you very much to the organisers for giving me this opportunity. It's my first ever String Pheno conference. It's been a delight to attend. I guess I'm one of the fresh young people that Gary mentioned in his speech last night. I've not been a fresh young person for ages, so it's nice to be able to embrace that. I'm going to tell you something that compared to the other talks I've seen is extremely simple and straightforward. It's a very basic fact about quantum field theory that I want to get across. And the message is the following. If you have a chiral gauge theory, let's say in 4 dimensions, a chiral gauge theory where left and right-handed fermions transform differently under the gauge group, then there is no obstacle at all to giving those fermions a mass, leaving the gauge group entirely untouched. And I have a poll on my screen, so let me just try and remove that. All right, very good. So there's no problem at all in giving a mass to the chiral fermions, not doing any damage to the gauge group. Now, depending on your background, this statement is probably either entirely obvious or utterly surprising. For me, it was certainly very surprising when I first realized it. If it's obvious, this is going to be a slightly boring talk for you. Let me remind you why it might be surprising. Because by definition, in a chiral gauge theory, you cannot write down a mass term for fermions. The left and right-handed fermions transform differently, and the mass term is not gauge invariant. And in the most familiar examples that we know of, the standard model being the standout example, the fermions do get a mass, but they get a mass only by coupling to a Higgs field. And when the Higgs field condenses, it gives a mass to the fermions, but it also necessarily breaks the gauge group. So that's sort of the intuition that I used to have, and I think many of us still do. And what I want to tell you is that intuition is very much rooted in weakly coupled quantum field theory. And that if you allow for strongly interacting quantum field theories, there are mechanisms which quite happily give masses to groups of chiral fermions, masses that can be arbitrarily large, can be much, much heavier, parametrically heavier than any scales associated to the gauge group. And I believe it should be possible to do this for any chiral gauge theory at all. So that's what I want to do. I want to give you some intuition at the beginning of this talk for why you should expect this to be true. And then at the end of the talk, I'll run through a very, very explicit example on how we can do this. So that's where we're going. Let me say this is based on 2 papers, one last year with Shlomo, and then another one a few months ago, just filling in lots of details, giving lots of examples. In the first paper in particular, we have lots of examples to do with subtle discrete symmetries and so forth. And such like. Here, I'm not going to talk about anything subtle at all, just very, very straightforward examples. All right, so the first thing to say is that there is a name for this phenomenon. It's a name that comes from the condensed matter literature, and the name is symmetric mass generation. So symmetric mass generation is the phenomena where a bunch of fermions get a mass, but they do so preserving a symmetry that you might naively think should have been broken. So typically a chiral symmetry. Before I get going, let me tell you some motivations, because there's actually a very, very long history of these kind of ideas. My main motivation came out of lattice gauge theory. So in lattice gauge theory, there's a very famous theorem called the Nielsen-Ninomiya theorem. And the Nielsen-Ninomiya theorem, roughly speaking, says you cannot put a chiral gauge theory on a lattice. In other words, you cannot simulate a chiral gauge theory on a computer. Here's the rough idea. When you discretize space, or in fact space-time, but space is sufficient. When you discretize space, momentum becomes a compact variable. It's what condensed matter physicists call the Brillouin zone. And if you try to put a chiral fermion on the lattice, you'll get a massless chiral fermion at the origin of momentum space. But there are topological arguments that say for a compact momentum space, if you have one massless chiral fermion, somewhere else in that momentum space, you have to have another chiral fermion of the opposite chirality. So it's what's called a fermion doubler. What this means is that if you try to put a chiral gauge theory on a lattice, the lattice rebels, it spits you back a vector-like theory, which is very different from the theory you wanted to simulate. It's a very powerful theorem. Taken at face value, the theorem tells us that we are not living in the matrix, because you can't simulate a chiral gauge theory on a computer, no matter how advanced an alien civilization you are. However, like all no-go theorems in physics, it has certain assumptions. And I think the general feeling of anyone who's thought about this is that it should be possible to circumvent this no-go theorem, although to date, no one has succeeded in doing that, at least not at the level of actually simulating chiral gauge theories. And the first, I think, real interesting attempt to do this dates back to the mid-80s and work of Eichten and Preskill. And Eichten and Preskill suggested the following. You have your momentum space, and you have the original chiral fermions at the origin, and then elsewhere at the edge of the Brillouin zone, you have the doublers. And the doublers are also a collection of chiral fermions. And they suggested that it might be possible to use strong coupling techniques to give masses to those doublers, leaving the original fermions alone. The loophole in Nielsen-Ninomiya, by the way, is that Nielsen-Ninomiya assumes weakly interacting quantum field theory. So I could tell you a lot about the Eichten-Preskill proposal. There have been many, many dozens of papers over the years exploring this. I think a fairly good summary is that it's a fantastic idea that simply doesn't fly. At least no one so far has succeeded in making it work. There are still people working on it. I could imagine that it could succeed in the future, but at the moment, it's not been made to work. A second motivation comes from condensed matter physics. There's a story of interacting topological insulators in condensed matter physics. And these are typically situations where there are discrete symmetries that protect fermions from getting a mass. Things like time reversal in odd dimensions, or some Z2 flips of left movers, but not right movers in even dimensions. And starting with the work by Fidkowski and Kitaev about 10 years ago, condensed matter physicists realized that you can give masses to fermions in groups of special numbers. So somehow in low dimensions, fermions in groups of 8 can get a mass while preserving these discrete chiral symmetries. And in higher dimensions, in groups of 16, it's closely related to what Jonathan Heckman was talking about in his talk. So these were very much in my mind when I started thinking about this and how it might apply to things more related to particle physics. It occurs to me, though, that for this audience, that there's another motivation, which wasn't mine, but might be yours, which is I learned from Miriam's talk that you have all these models with extra exotic chiral matter. And somehow the punchline of this talk is that there should absolutely be a way to gap that chiral matter, leaving the standard model alone. I appreciate you've already got like a gazillion things without chiral matter, but you know, if you want something to do on the weekends, Miriam, then there should be a geometrical realization of what I'm going to explain. All right, so with that motivation out of the way, let me give you some intuition for why it should be possible to gap chiral fermions. So the first thing to say is there is an obstacle to when you can gap fermions preserving certain symmetries. And the obstacle isn't new. It was understood by Toft back in the early 80s, at least for continuous symmetries. And there's been a lot of work in the last 10 years understanding the analogous things for discrete symmetries. Here I'll just talk about continuous symmetries. And the idea is the following, that if you have a symmetry with a global symmetry, sorry, I said the word wrong. If you have a theory with a global symmetry G, then there is a number that you can associate to that symmetry called the Toft anomaly. And if it's a continuous symmetry, this number is got just by summing over these triangle diagrams. Now, I should stress this is not the ABJ anomaly. If this number is non-zero, it doesn't mean the symmetry isn't a good symmetry of the quantum theory. It's absolutely a good symmetry. But this Toft anomaly is a way to characterize the symmetry in a given theory. And the important point is that the Toft anomaly is completely robust to deformations of the theory, and more importantly, to RG flow. So whatever you do to the theory, if the symmetry G survives, this Toft anomaly remains unchanged. It's also true that this Toft anomaly is an obstruction to gauging. If the Toft anomaly is non-zero, you're not allowed to promote that global symmetry to a gauge symmetry. Now, this Toft anomaly is the real obstruction to gapping fermions. In particular, if you have a continuous symmetry and the Toft anomaly is non-zero, then there's no way to give a mass to those fermions while preserving the symmetry G. And the reason is the following, that you give a mass to the fermions preserving the symmetry G, but if you look at energy scales below that mass, there's nothing to tell you about the Toft anomaly. The Toft anomaly should be RG invariant. I should add that for discrete symmetries, you might get a topological quantum field theory in the infrared, but for continuous symmetries, that's not an option in 4 dimensions. So you cannot gap fermions preserving any symmetry G that has a Toft anomaly. However, if the symmetry does not have a Toft anomaly, the Toft anomaly vanishes, then there should be no obstruction. And in particular, if you have a chiral gauge theory, you know the Toft anomaly vanished because you went ahead and gauged the symmetry. So whenever you have chiral fermions, either in a global symmetry with no Toft anomaly or in a gauge theory, there should be no obstacle whatsoever to giving them a mass preserving the symmetry. And the question is, how do you actually do it in principle, in practice? So that's what I'm going to tell you. All right, so here's the basic idea. This can all be found, the details can all be found in the paper I wrote with Shlomo last year. Take your favorite chiral gauge theory in 4 dimensions. And if your favorite chiral gauge theory in 4 dimensions is the standard model, all for the best. So what's the deal? It's a chiral gauge theory, so you cannot write down bare mass terms because they're not gauge invariant. You can write down Higgs mechanism, but that's exactly what we want to avoid to give masses to these fermions. And you can probably, in most cases, write down 4 fermion interactions that are gauge invariant. If not 4 fermion, maybe 6 fermion or 8 fermion interactions that are gauge invariant. But those higher fermion terms are always going to be irrelevant operators. So they're never going to do the job for you of mapping the fermions, which is what you want. It's worth saying that Eichton and Preskel on the lattice tried to work with these irrelevant operators to gap fermions, but as I said earlier, it seems not to work. All of which means that if we've just got the chiral gauge theory and nothing else, those massless fermions really are stable, and there's no way to give them a mass while preserving the gauge symmetry. So the game we have to play is to embed our original chiral gauge theory in a slightly larger theory. So here's the setup. I want to consider the original chiral gauge theory, but in addition, I'm going to consider a whole bunch of extra massive states. These massive states may, in some situations, be charged under the original gauge group, but if they are, they have to come in vector-like pairs, because I want to just be able to write down a generic standard tree-level mass term and be able to make that mass arbitrarily large so that if I wanted, I could just decouple these extra states and make them as heavy as I like. So original stuff plus some extra vector-like matter. That's our starting point. And now what we do is the following. We dial the parameters of the theory. And the goal is to dial the parameters so the extra heavy stuff starts to become light. At some point, it's going to interact with the original chiral stuff. And you want to design things so that when the dust settles, all the chiral stuff down here has turned into a vector-like matter and become heavy. And what you're left with in the far infrared, if anything at all, is just vector-like matter. That's the game that we're going to play, all of which relies on the following very unlikely looking equation. It's that if you take a chiral-like theory and add to it a vector-like theory, the end result could be a vector-like theory, which somehow smells wrong. You know, it feels like chiral plus vector should always be chiral. But as I mentioned before, the way you characterize symmetries is by the Toft anomaly. And by construction, the Toft anomaly here vanishes on both the left and the right-hand sides of this equation. So we'll see examples as we go on that chiral matter plus vector matter can actually rearrange itself and transmute into something that's just vector-like. So let me sort of flesh out some details. I'm going to build towards an explicit example, but I'll fill in some details about how this this could work. Again, sort of slightly generic at this point. So suppose you have a bunch of massless fermions, and suppose they transform in some chiral representation of a symmetry that I'll call G. And for the sake of argument, I'm going to take 3 left-handed chiral vial fermions and a single right-handed chiral fermion. All right, the idea is that among that heavy degrees of freedom that I'm going to bring down and make light is some strongly interacting stuff. And I'm going to make this stuff interact just with a subset of these fermions. And for the sake of argument, let me suppose I make it interact just with the left-handed fermions, and the right-handed fermion just stays to one side and doesn't engage in this conversation for now. All right, so it may be possible in certain circumstances to introduce some strongly interacting force that binds these fermions together, these 3 fermions. And what you want to achieve is some way that those 3 fermions bind together with some confining force to give a new massless left-handed fermion that I call psi nu. Now, this is not typically what happens with confinement. Typically, if you have confinement, the fermions that you end up with at the end of the day are massive. Proton and neutron in QCD are very clearly massive. So it's not generic, but it is possible to cook up situations where this happens, where you get massless composite fermions in the infrared after confinement. If you can find a way to get this new fermion to have exactly the same quantum numbers as psi r, then your job is done. You see, none of the original 3 had the same quantum numbers as psi r. That's the statement that this was a chiral representation of G. But if this bound state has the same quantum numbers as psi r, which is possible, you can add in the UV the following 4 fermion interaction. Now it's invariant under G because these 3 fermions, the left-handed fermions, transform in the same representation as psi r. So this is a singlet. It looks like it's an irrelevant operator, but because of this strong coupling dynamics, it's an example of a dangerously irrelevant operator. Meaning it looks irrelevant in the UV, but by the time you flow to the infrared, you realize that actually it's a relevant operator. And what happens is these 3 fermions bind together, and they bind together to a new fermion so that in the far infrared, effectively, this is just a mass term. But it's a mass term that by construction gaps everything, preserving G. So this is the general strategy that we can use in order to gap chiral fermions. Let me say that there's a catch. The catch is the following. Usually in theories that confine, confinement comes hand in hand with chiral symmetry breaking. And from the perspective of what we want to achieve here, that's bad. That's bad because the symmetry that is typically spontaneously broken turns out to be precisely the symmetry G that you are hoping to preserve to begin with. So what this means is that if you want to find ways to enact symmetric mass generation in 4 dimensions, the way you achieve it is by theories that have confinement, but no accompanying chiral symmetry breaking. And these theories are rare, but they're not unheard of. And in particular, in supersymmetric theories, we have a whole list of such theories that do the job. All right, so in the last 5 minutes, let me just give you a very explicit example of how we can do this. The example's not quite the simplest, but it's not far off from being the simplest. And moreover, I think it's clearly the most interesting. So it's to take one generation of the standard model, 15 fermions with very familiar quantum numbers under SU3 times SU2 times U1, and find a way to give them a mass without breaking SU3 times SU2 times U1, and in particular without breaking electroweak symmetry. Obviously, nature chose to give them a mass in a different way. I don't know if how this is relevant for phenomenological purposes, although it would be very interesting to explore to see if there was. But just as a proof of principle, I'll show you how you can give all these fermions a mass without breaking electroweak symmetry. All right, so hopefully the quantum numbers are familiar. I multiplied the hypercharge by a factor of 6, so all the hypercharges as the subscripts are integers. I've also taken the left-handed fermions and conjugated them. So everything that's written here is a right-handed fermion, which, if you can't remember the minus signs on hypercharges, the only sign of that is that there's a 3 bar that sits here. All right, so to give these a mass, I have to do 3 steps. So we'll do this in turn. Step number 1, I need to introduce some heavy extra degrees of freedom. And those heavy extra degrees of freedom are going to be 3 further pairs of fermions. So these fermions are in red. Notice that they come in pairs and the pairs are vector-like. So they have conjugate quantum numbers, which means there's no problem at all in me just writing down a bare mass term to everything in red and making them very, very heavy, as heavy as I like to begin with. All right, so that's step number 1, add the heavy massive degrees of freedom. Step number 2 is to notice that having added this extra degrees of freedom, there are some objects that appear twice. Everything in the green box appears twice, which means that in adding the extra degrees of freedom, I've introduced the possibility for a new SU2 symmetry. So I'm going to call this new SU2 symmetry H to distinguish it from the weak force that sits in the standard model. Importantly, you can check that H has no mixed anomaly with hypercharge, which means that both are simultaneously good symmetries. Now, to begin with, all the red stuff was heavy and all the black stuff was light, which means to begin with, there was no SU2 symmetry. What I'm going to do, however, is introduce gauge bosons for this SU2. But because there was no SU2 symmetry to begin with, initially it's going to be Higgsed. So I'm also going to introduce a scalar field, not charged under G, that's important, just charged under H, that condenses and breaks the symmetry precisely to allow the red stuff to be heavy and the black stuff to be light. Okay, so this is my heavy degrees of freedom, the red fermions plus some SU2 Higgsed gauge bosons. And now what I do is take this scalar and just uncondense it and then make it heavy and decouple. As the scalar uncondenses, the SU2 gauge bosons come down. And at some point, I have some massless SU2 gauge bosons interacting with a bunch of fermions, which are the fermions in the green boxes. And I'm going to have to figure out what the dynamics of this SU2 gauge theory is. Brent, you've suddenly appeared on my screen. Do I have 3 minutes left?
Exactly 3 minutes. Thank you.
Good. I'm going to finish in exactly 3 minutes. All right, so what's the deal? I have to solve the dynamics of an SU2 gauge theory coupled to a bunch of matter. How much matter? There are 6 doublets of fermions. There are 6 because there are, I've lost my cursor, there it is. There are 2 in this green box, there are 3 in this green box, and there's 1 in this, this final box. Now, SU2 coupled to 6 doublets has an SU6 symmetry, a flavor symmetry that rotates those doublets. And it's not hard to see that the standard model group G is embedded within that SU6. All right, so what happens? This SU2 will confine, but what happens is not good. We know what this theory does from some sort of fairly naive expectations, but also from lattice simulations. This can be simulated on the lattice. What happens is the SU2 confines, but the SU6 global symmetry is spontaneously broken down to SP3. That means that when SU2 confines, the global symmetry is broken, but that means that you also spontaneously break the standard model. So this does not do the job that we want. However, it's not hard to fix up, and this is where the third element comes in. To fix it up, what you have to do is take everything on the screen and make it supersymmetric. That means that I'm going to add some scalar superpartners for all the fermions here. Again, they can be heavy to begin with, but I'm going to bring them down and make them light as ideal parameters. And in addition, I should add an extra fermion, which is the gaugino for H, not charged under the standard model, just charged under H. Now what happens? Now the dynamics is the dynamics of a supersymmetric SU2 theory coupled to 6 doublets. And this is a very famous theory. It's among the class of theories that Natty Seiberg first solved in the 1990s. And it does exactly what we want. It's one of those supersymmetric theories that confines, but without breaking the SU6 global symmetry. In other words, without breaking the standard model from the perspective of this setup. So what does it do? There are 6 objects in the green box. And after confinement, these objects in the green box get stuck together to form meson states. But these meson states are fermions because it's a scalar bound with a fermion. So there are 15 such meson states, 15 because there's some anti-symmetry, so it's 6 times 5 divided by 2. And I've just listed them on the bottom. These are all the anti-symmetric objects you can make from things in the green boxes. In addition, there are also 15 particles that didn't play a role in any of this. These are the 15 particles that aren't in green boxes. There's 2 here, plus 6 here, plus 1, plus 3, plus 3. And the wonderful fact, which you can check, is that the quantum numbers of the 15 bound states are exactly conjugate to the quantum numbers of the 15 objects that weren't involved in this whole dynamics. Which means we can go to our theory and we can add the following cubic superpotential. It's a superpotential which is constructed to be invariant under the standard model gauge group. And each term in the superpotential contains 2 objects in green boxes and 1 object that is not. But as you flow to the infrared, the SU2 confines and the 2 objects in green boxes bind together to become a new effective massless superfield, which are the tilde objects. And what you end up with at the end of the day is simply a mass term for everything in the standard model. So it's a very explicit construction that takes one generation of the standard model, admittedly makes it interact with extra vector-like degrees of freedom, but the upshot is that at the end of the day, all you have is massive vector-like degrees of freedom. Everything in the standard model has become massive. The standard model gauge group completely unbroken. Brent is back, so I should finish. Let me just finish by saying I used supersymmetry, but I used supersymmetry not because I'm desperate for the world to be supersymmetric. It was simply a crutch. It was a crutch to give me some handle on strong coupling dynamics. It's also a crutch that we can dispose of. This whole mechanism survives if you do soft supersymmetry breaking, as long as it's not too big. I don't know how big it can be before it breaks, but it's absolutely not a mechanism that relies on supersymmetry. It's just a general mechanism of strongly interacting field theories. All right, so that's all I have to say. If you have a chiral gauge theory, it is possible to give masses to matter without breaking the gauge group. And I'll finish there. Thank you very much for your attention.
All right, thank you. I was following the narrative so closely, did not want to interrupt you, so thanks. We have time for some questions. And I'm trying to see hands raised or just speak.
There's an Ivano who's raised his hand.
Yes.
Okay, go
yeah,
for
that's
it.
me. Hi.
Hi, Ivano.
Hi, hello. Thanks for the very nice talk. I was wondering, so how exactly does the story change, if it does, in 1+1 dimensions, apart from this 8 groupings of 8 fermions that you mentioned in the beginning?
If you have continuous symmetries in 1+1 dimensions, the story is very different. It's very different because you have the Mermin-Wagner-Coleman theorem, which tells you can't spontaneously break continuous symmetries in 1+1 dimensions. So then the problem comes, can you just find relevant operators in the game that will gap the system? And in the paper from April, I have many examples. It's much more subtle with discrete symmetries, but that's really what Fitkowski and Kitai have understood in
right. Okay. No, thanks a lot.
James.
So, yeah,
sorry, I'm doing your job, friend.
So that's fine.
Hey, David, beautiful talk. Yeah, so I noticed and liked your paper. So my question is sort of about thinking about the broad set of gauge theories that we get in string theory. One might like to have some conditions either necessary and sufficient for this working. in some sense, you wrote down a 1-generation standard model, and then there were these extra clever things you did on top of it. But if I just handed you an arbitrary chiral gauge theory and then asked, is there something you can do to it with this combination of vector pairs and other condensation that's going to ensure that you can or can't do this? Do you have any comments along those lines in terms of conditions?
At the moment, it's an art.
Yeah.
I've tried to do it for everything that I've seen that's out there. I've succeeded in all but one case. SO10 with a 16. I have not succeeded in gapping that 16, preserving SO10. I suspect it's because I'm not smart enough, but it would be much more interesting if there was an additional obstruction that I've missed. My general feeling is that the obstructions are Toft anomalies, and if the Toft anomalies vanish, it should be possible to achieve this. But I don't have an algorithm where you turn a handle and it works. Right,
but so in the logic, the Toft anomaly is one potential obstruction, but in principle, there could be other obstructions that just haven't been come up with yet.
There could certainly be other Toft anomalies that we haven't understood, and we've discovered lots in the last 10 years. So if there was an obstruction, it would be very interesting. Let me say that.
A related question: you focused on 1 generation just to make life easier, or does something go wrong with multiple generations?
You can do them one at a time. You could also ask, can you do it preserving the flavor symmetry of those multiple generations? That's something I used to know the answer to, and embarrassingly, I don't now. But it was something we thought about. I think the answer is yes, but it's yes with some error bars. Yeah. Sorry.
Thank you. I see another hand up, so I'll let John ask his question.
Yeah, I have to be quick.
Hey, thanks for the great talk. Can you comment on the relation to the 3-2 model of supersymmetry breaking? Because that involves something close to a single generation, and I was a little confused about there. They say that there's an ADS superpotential generated non-perturbatively, so I was curious about how come that doesn't apply in this situation.
I don't know. Maybe I've misunderstood the issue. So there was no 3-2 dynamics here. So it's not the SUSY breaking. Dynamics was just SU2. It wasn't. Said another way, the dynamics of the gauge theory I called H, the auxiliary gauge theory, was entirely vector-like. It's not chiral dynamics that we're doing here. It's vector-like dynamics to gap chiral fermions.
Understood.
There is another way to interpret your question, which wasn't quite what you meant, but the usual SUSY breaking story is you don't get SUSY breaking in vector-like theories because you can gap them, and the Witten index therefore is obviously non-zero. But you can also gap chiral-like theories. So I don't quite understand how this fits in with the wider picture of when supersymmetry is broken and when it's not. But it's certainly something that I'd like to explore.
I should probably cut you off. Thanks again, David. Great